Welcome to an exploration of one of the most fascinating phenomena in nanoscience, the magnetic size limit. As we shrink magnetic materials down to the nanoscale, something remarkable happens. Their magnetism fundamentally changes. Before we understand what happens at the nanoscale, let's review magnetism at the atomic level. Magnetism fundamentally arises from two sources, the intrinsic spin of electrons and their orbital motion around atomic nuclei. Each electron acts like a tiny magnet with a magnetic moment pointing in a specific direction, represented by this arrow. The magnetic moment mu equals the G factor times the Bohr magneton times the spin quantum number. In ferromagnetic materials like iron, cobalt, and nickel, neighboring electron spins naturally align parallel to each other. This creates regions called magnetic domains where millions of atomic spins point in the same direction, producing a strong net magnetic field. To understand the size limit, we need to understand magnetic domains in bulk materials. A magnetic domain is a region within a ferromagnetic material where all the magnetic moments are aligned in the same direction. A typical piece of iron contains many domains with different magnetization directions. The arrows in each domain point the same way, but different domains point in different directions. Between domains are thin boundaries called domain walls, where the magnetization gradually rotates from one direction to another. The total energy of a magnetic system includes exchange energy favoring parallel spins, anisotropy energy from crystal structure, and magnetostatic energy from magnetic fields. Domains form because this multi-domain configuration minimizes the total magnetic energy of the system. Now we arrive at the crucial question: what happens as we make a magnetic particle smaller and smaller? Here's our key question. Can a magnetic particle become so small that it can no longer support multiple magnetic domains? The answer is yes. As particles shrink, we transition from multi-domain to single-domain, and eventually to superparamagnetic behavior. Let's calculate the critical size where a particle becomes single-domain. Creating a domain wall requires energy because spins must rotate gradually from one direction to another. The domain wall energy equals the wall energy density gamma times the wall area A. The wall energy density is approximately the square root of the exchange constant A times the anisotropy constant K. When a particle becomes small enough, the energy cost of creating even one domain wall exceeds the magnetostatic energy saved by having multiple domains. The critical diameter for single domain formation is approximately 72 times the square root of A times K divided by mu0 times the saturation magnetization squared. Let's calculate this for iron with real numbers. For iron, the exchange constant is about 2 times 10 to the minus 11 joules per meter. The anisotropy constant is about 5 times 10 to the 4th joules per cubic meter. The saturation magnetization is about 1.7 times 10 to the 6th amperes per meter. Plugging these values in, we get a critical diameter of approximately 15 nanometers for iron. This means that below about 15 nanometers, an iron particle cannot support multiple domains and becomes a single-domain magnet. Now we reach the heart of our topic, superparamagnetism, where magnetism loses its memory. Here's the critical question: can thermal energy at room temperature flip the entire magnetization of a single-domain nanoparticle? The answer is yes, if the particle is small enough. This is superparamagnetism. Imagine a single-domain nanoparticle with its magnetization pointing up at time zero. A short time later, thermal fluctuations have caused the entire magnetization to randomly flip to a different direction. The magnetization direction fluctuates randomly between different orientations, driven by thermal energy. This behavior is analogous to paramagnetism in individual atoms, but now it's the entire nanoparticle acting as a single giant magnetic moment. To understand when superparamagnetism occurs, we need to examine the energy barrier to magnetization reversal. Magnetic anisotropy creates an energy barrier that the magnetization must overcome to flip from one orientation to another. The anisotropy energy barrier equals the anisotropy constant K times the particle volume 5. This creates a double-well energy landscape. The magnetization sits in one of the two energy minima, separated by an energy barrier. Thermal energy provides random fluctuations that can kick the magnetization over this energy barrier. The relaxation time tau equals tau0 times e to the power of kV over kBt, where tau 0 is typically 10 to the minus 9 seconds. This is the famous Néel-Arrhenius equation that describes how quickly the magnetization flips. The transition to superparamagnetism is characterized by the blocking temperature. At what temperature does a given nanoparticle transition from blocked, stable magnetization to superparamagnetic behavior? The blocking temperature equals kV divided by Boltzmann's constant times the natural log of the measurement time over tau 0. Above the blocking temperature, the particle is superparamagnetic with rapidly fluctuating magnetization. Below the blocking temperature, the magnetization is frozen or blocked in a particular direction. Let's calculate the blocking temperature for a spherical iron nanoparticle. For a 5 nanometer diameter sphere, the volume is about 6.5 times 10 to the minus 26 cubic meters. Using the same anisotropy constant of 5 times 10 to the 4th joules per cubic meter. Plugging into the formula with a typical measurement time of 100 seconds. We get a blocking temperature of approximately 6 Kelvin. Since room temperature is about 300 Kelvin, this 5 nanometer iron particle is definitely superparamagnetic at room temperature. The blocking temperature has a strong dependence on particle size. The blocking temperature is proportional to volume, which scales as diameter cubed. This cubic dependence means that blocking temperature increases very rapidly with particle size. A small change in diameter produces a large change in blocking temperature. Let's compare 5 nanometer versus 10 nanometer iron particles. The 5 nanometer particle has a blocking temperature of about 6 Kelvin. Doubling the diameter to 10 nanometers increases the blocking temperature 8-fold to about 48 Kelvin. Because volume scales as diameter cubed, doubling the diameter increases the blocking temperature by a factor of 8. Now we can understand what it means for a magnet to lose its memory. What do we mean when we say a magnet has memory? Magnetic memory is the ability to retain a particular magnetization direction even after an external magnetic field is removed. A blocked particle maintains stable magnetization, like a permanent magnet. A superparamagnetic particle has no magnetic memory. Its magnetization direction constantly changes. In practical terms, superparamagnetic particles show zero remanence, meaning zero retained magnetization, and zero coercivity, meaning no resistance to demagnetization. The hysteresis loop for a blocked particle shows a wide loop with remanence and coercivity. For a superparamagnetic particle, the loop collapses to a reversible curve with no hysteresis. Let's calculate the size below which particles become superparamagnetic at room temperature. For a particle to maintain stable magnetization at room temperature, its blocking temperature must be above 300 Kelvin. Setting the blocking temperature equal to 300 Kelvin, we can solve for the critical volume. The critical volume equals 300 times Boltzmann's constant times the logarithm factor, divided by the anisotropy constant. Using iron's anisotropy constant of 5 times 10 to the 4th joules per cubic meter, we get a critical volume of about 2.5 times 10 to the minus 24 cubic meters. Converting to diameter for a sphere, this gives approximately 17 nanometers. Therefore, iron nanoparticles smaller than about 17 nanometers are superparamagnetic at room temperature and cannot store magnetic information. The superparamagnetic limit varies dramatically with material choice. Different magnetic materials have vastly different anisotropy constants, leading to very different size limits. Iron has an anisotropy constant of about 5 times 10 to the 4th joules per cubic meter. Cobalt has a much higher anisotropy of about 5 times 10 to the 5th joules per cubic meter. Samarium cobalt-5 has an extremely high anisotropy of about 1.7 times 10 to the 7th joules per cubic meter. Materials with higher anisotropy can maintain stable magnetization at much smaller sizes. The critical diameter scales inversely with the cube root of the anisotropy constant. Because cobalt has 10 times higher anisotropy than iron, cobalt particles can be about half the size while maintaining the same blocking temperature. Understanding the magnetic size limit has crucial practical applications. In magnetic hard drives, we want to pack data bits as densely as possible, but each bit must be large enough to avoid superparamagnetism. Each tiny magnetic region stores one bit of data. As we shrink these regions to increase storage density, we approach the superparamagnetic limit. The superparamagnetic limit fundamentally constrains the maximum data density achievable with conventional magnetic recording. Interestingly, superparamagnetism is actually advantageous for some medical applications. Superparamagnetic iron oxide nanoparticles are used as contrast agents in magnetic resonance imaging. They magnetize strongly in the presence of an MRI magnetic field, enhancing image contrast, but don't permanently stick together when the field is removed because they have no remnant magnetization. How do scientists experimentally detect and characterize superparamagnetism? The most common method is measuring magnetization as a function of temperature. Magnetization, measured after cooling in a field, shows a sharp drop at the blocking temperature as particles transition from blocked to superparamagnetic state. Magnetic susceptibility measurements at different frequencies can probe the dynamics of magnetic relaxation. Mössbauer spectroscopy provides direct information about magnetic relaxation on timescales from nanoseconds to seconds. Several theoretical models help us understand and predict superparamagnetic behavior. The Stoner-Wolf model treats a single-domain particle as a single giant magnetic moment that rotates coherently. The energy depends on the angle theta between magnetization and easy axis, including both anisotropy and Zeeman terms. This model provides the energy landscape that determines the barrier height for magnetization reversal. Néel-Brown theory extends this to include thermal activation over the energy barrier. The attempt frequency for jumping over the barrier follows an Arrhenius-type exponential dependence on temperature. Real nanoparticles often deviate from simple theoretical predictions. As particles shrink, surface atoms become a larger fraction of the total, and surface effects dominate. Surface atoms have fewer neighbors and broken symmetry, leading to different magnetic properties than bulk. A nanoparticle consists of a core with bulk-like properties and a surface shell with modified magnetic behavior. Surface effects can either enhance or reduce the effect of anisotropy, depending on the material and surface chemistry. In real systems with many nanoparticles, magnetic interactions between particles can significantly modify the superparamagnetic behavior. These interactions can lead to collective behavior and complex spin glass-like states at low temperatures. Let's summarize the key points about the magnetic size limit. First, magnetism originates from quantum mechanical electron spins in atoms. Bulk magnets form multiple domains to minimize their total magnetic energy. Below a critical size of tens of nanometers, particles cannot support domain walls and become single domain. At small sizes, thermal energy becomes comparable to the anisotropy energy barrier. Below the blocking temperature, magnetization remains stable in one direction. Above the blocking temperature, the particle enters the superparamagnetic regime, with rapidly fluctuating magnetization. The blocking temperature scales as diameter cubed, depending on the anisotropy constant K. The superparamagnetic limit varies with the material's anisotropy constant. Materials with higher anisotropy have smaller critical sizes for superparamagnetism. Understanding superparamagnetism is crucial for designing and optimizing magnetic nanoparticles for applications.